Hi, everybody. I'm going to carry this if I can. So this talk is going to be about extending Kubernetes, and specifically, I'm going to be talking a lot about how to, about the architecture of Kubernetes and how you would build, extensions or operators for Kubernetes to extend functionality. So my name is IanMLewis. I'm a developer advocate at Google. I work here in Tokyo, Japan. And I have a background kind of in Go and in Python development, as well as in infrastructure, particularly related to containers and Kubernetes. So I'm going to kind of talk about, the problem that we're going to be kind of solving by extending functionality of Kubernetes. But just to kind of get a vague understanding of where everybody is, how many people have actually used Kubernetes and have touched it before? Okay. About like 30 to 40%. Okay. So Kubernetes is kind of is a container orchestration system, or it's a management system for containers. And this kind of environment is one where you kind of deploy an application to the system and it gets scheduled onto a machine. But those applications are run in kind of in a fairly dynamic manner. And Kubernetes is able to kind of self-heal these applications. And so that presents a number of challenges because applications can fail at any particular time, and then they could be moved and restarted somewhere else. The IP addresses for those particular instances of the application could change. Also, you might scale up or down an application, or maybe the application auto-scales and adds new instances. And so you want to be able to dynamically deal with that, or deal with that kind of dynamic system. And Kubernetes provides some building blocks to help you with this, but it doesn't provide complete solutions for particular applications. So particularly things that hold state, like databases, are challenging. Other ones where Kubernetes would need to know a little bit about a particular application's network protocol or something like that, are things that Kubernetes cannot provide, like full, complete solutions. So Kubernetes also provides new kind of APIs and constructs that it uses for providing infrastructure to people and to the end users. But these are kind of new API constructs, and it's kind of challenging to use them, and there's a learning curve to using them. And particularly when you're trying to extend Kubernetes, you need to really kind of understand the API itself in order to use it and extend Kubernetes properly. So I'm going to go through kind of an example, a very simple example, and it's a little bit contrived. But if you'll bear with me, hopefully this is instructive of the type of situations you would run into when you're trying to automate something in Kubernetes. So the problems with deploying something like Memcache into Kubernetes is that Memcache is typically sharded or load balanced to different instances by hashing the key that of a particular piece of data that you're entering in the cache, or you're sending in the cache. And so when you go to get that particular piece of data, the key is also then hashed to decide which server to go to get the data. And so in order to know which server to talk to, you need to have some knowledge about the protocol. You need to know that this is a key value type of store. This is something that you need to know what the protocol looks like in order to parse it and figure out which server you need to talk to. And so you can get, you can't provide a very simple solution where or a simple endpoint that you can connect to, that an application connects to, in order to just connect to our memcache. Memcache also, because of that, like needs some kind of service discovery. So the client side needs to know the list of IP addresses so it can then hash the key to a particular IP address or to a particular server. So, ideally we don't want to have to update our application code to add in all of this logic to do service discovery and whatnot, and then depend on talking to the Kubernetes API or something like that in order to get back the list of servers. We want to be able to just connect to a particular, like ideally a single IP address and port in order to talk to our cache. We also want to be able to support like different types of topologies usually, but like, this is kind of a nice to have, but you want to be able to support lots of different types of topologies without having to like push all that application configuration down to each individual client. So here's like a very simple way of, you might deploy it. Just deploy a proxy in front that handles all of the hashing of the key, and that can then know about the backend servers. And so we can think of kind of automating, when we want to automate something, we can think of how we would actually configure it if we were doing it kind of manually ourselves. So let's kind of run through this example. So first, we're going to create a deployment to deploy our proxy, and a deployment is just a way of deploying multiple instances of an application. Then we're going to configure the proxy using a config map, which stores configuration in a file, which the proxy can then read. And then when the backends change, like say our memcache instances change, like the IP addresses or whatnot, we can then update the config map and then update the proxy. So we have something like this right now, where we have a deployment that's now pointing to this like config map conf v1, and it has the list of the 3 IP addresses for our backends. So then what happens, like say when our backends change, like we scaled down our backends to 2 instances, what we can do is we will create another config map with the new configuration. So in this case, we just say like it's v2. And then we update our deployment to point to the new config map. So if it now points to config v2. And then once we've done that, the deployment will then trigger a rolling update. So the instances will actually roll over, or it will create a new version of the instance, essentially restarting the proxy server to then use the new configuration and talk to our instances. Okay, so this is great, but this is something that you wouldn't necessarily want to have to do every single time that you scale up or down your memcache cluster, or whenever one of the IP addresses changes, or that sort of thing. You want to be able to do this in an automated way. So how would we kind of support an application like memcache? And how we would do that is we build something called an operator, which will essentially implement some piece of operational knowledge, some piece of operational automation that we want to do, and use the Kubernetes API to do all of the things that we just went through. So before we talk about like exactly how you would do that, I'm going to kind of take just a step back and talk about the API itself. So I want to do kind of a quick Kubernetes API primer and talk about like just the architecture of the Kubernetes API. So the Kubernetes API is kind of normal REST interface. They also have a gRPC interface, but most end users would not use that. But so each object in the Kubernetes API has a set of common properties that all objects have. So one of those is the API version. The API version specifies a group and a version. So this group and version is used to kind of help identify that particular type of object. And essentially the API endpoint that you use to talk to. The kind is just specifying the type of the object. Then based on this and the API version, you can know what type of object it is and essentially the format of that particular object. The next like common piece of each API object is metadata. So metadata includes the name of the object itself, and then labels, which are just essentially a key value type set of labels, and these are kind of optional. You can use these any way you want to, and these can be used to kind of query and select objects later. So you can kind of filter on the objects to kind of get the ones that you want. So in this case, you might filter on, say, like app equals nginx, and you would get just the deployments that have nginx, or app equals nginx in the labels. Another kind of important thing, so when you're extending the API, is owner references. Normally when you're using Kubernetes, you don't really care about these too much. But when you're extending Kubernetes, this is a very useful construct in that you can create objects that depend on other objects and then specify a reference to the other object or to the parent object. And so this can kind of create a dependency tree of objects within the API. And you can use this later to say when you delete the deployment in this case, these like replica sets that are owned by the deployment can then be garbage collected automatically without you having to delete every single object. So this is really helpful like for end users because they just basically create a deployment and then all of the owned objects are created by, say, operators or controllers that are running in the cluster automatically as part of some piece of automation. So the end users only care about the deployments. They don't have to care about all of the other objects that get created in the cluster. And object owner references look like this. They just specify the kind and the name and the UID of each object, or the object that it references. And you can have multiple ones of these. So if one object is owned by multiple other objects, all of the owned objects would need to be deleted before the owned object is automatically deleted. All right. So we've kind of gone over that. Now I want to talk about the API and the architecture of Kubernetes itself with the API. And I like to describe the API as kind of a spoken wheel system. So you can think of the Kubernetes system as a wheel with spokes, kind of like a bicycle wheel, where the API is a hub in the center, and you have each spoke connecting to some client on the rim of the bike or the bicycle wheel. So since the Kubernetes API or the Kubernetes logo looks kind of like a wheel, we're going to show it as a kind of illustrate that here. So you have something that looks something like this, where you have the API server in the center, and then you have a bunch of API clients all around the edge. And essentially, what a lot of these clients, the form that each of these clients, or the architecture of each of these clients, is generally takes the form of a controller or a control loop. And so in Kubernetes parlance, we call these controllers, or we call each control loop a controller. And what these do is they perform a loop that runs kind of essentially constantly. And so what it does is it observes a particular the state of the cluster, as well as the desired state of the cluster. So when you are using the API and you post a deployment or some other type of object, you are essentially declaring this is the desired state. This is what I want to happen in the cluster. And then the controller's responsibility is essentially to make that true or to implement that in the cluster. So what it does, the controller will do is take a look at the desired state and the actual state of the cluster. And if those differ in some way, it will act in order to make the desired state and the actual state equal. So if the desired state is like, I want 3 instances of my application running, and it looks at the state of the cluster and there's 2 application instances running right now, it will add 1 new application instance. Or maybe well, I'll talk about some of the other kind of examples a little bit later. But when you get down to it, the API server, essentially what you're doing when you're observing is you're getting or watching a particular object from the API server, watching it for changes or just getting the current state, and then diffing that with some other kind of state of the cluster. So that might not necessarily be through the API, but it might be through some other application or some other thing running, like some other way of running in the cluster, like maybe some statistic or something coming from some other system. And then at the end, you update generally back into the API server, like some sort of, create a new object or that sort of thing, or update the status of some object. So this is typically like kind of what you see when you see controllers. So Kubernetes itself, like all of the built-in objects in Kubernetes, or the built-in components of Kubernetes, sorry, are generally kind of follow this pattern. So there's many built-in clients that are part of Kubernetes that follow a pattern that's very similar to this. So some instances are like the kubelet, the kube proxy. Controller manager actually contains a bunch of different controllers, as well as the scheduler. So the scheduler is responsible for scheduling pods to individual nodes. And so each one of these, like kind of all of the built-in clients all follow this kind of pattern of having a controller that implements some sort of state or implements some sort of desired state in the cluster. Okay. So let's talk about how like controllers work and about a little bit about the kind of built-in controllers that we have in Kubernetes. So let's go kind of through an example of actually just deploying an application to Kubernetes and seeing what actually happens when we're deploying an application. And we'll see kind of how all of the controllers kind of work together in order to implement a full system. So first, we're going to create our deployment object, and this is going to have included in it what type of application I want to run and how many instances of the application that I want to run. So once that's created, our deployment controller will then see this particular object that it's created, and it will notice that none of the objects that it needs to create have been created yet. So it goes ahead and it creates something called a replica set, which is a separate type of object. And what a replica set is just essentially a list of, or a set of objects, or it represents a set of pods. So instances of the application. So you might ask a little bit, what's the difference between a deployment and a replica set? And really the only difference is that deployments also give you some other features like rolling updates and stuff like that that are kind of independent of the just managing a number of instances. So what we can do is, after this replica set gets created, our replica set controller then looks at that and says, okay, based on the number of replicas that I want in my replica set, I will create a number of pods here. And these pod objects are also just objects in the API. And so these get created initially with a particular name, but they're not yet scheduled to run on any particular node in the cluster. So what happens is our scheduler, which is another kind of controller, notices that, oh, like I have some pods that I need to run in the cluster somewhere. And it notices that these particular pods are not scheduled yet, and so it goes ahead and schedules them. It picks a, it monitors the cluster to find out where, which nodes have open resources, so like CPU and memory, and then finds a node that's appropriate for that particular pod, and then assigns that node name to the pod. So once the node name has been assigned, the kubelet, which is a separate type of controller, which runs on, is actually an agent that runs on each node in the cluster. Each one of the kubelet instances knows its own particular node name. And so it sees that the one for node 1 says, oh, okay, there's a pod out there that's assigned to me that is not running yet. So it sees that, and it says, okay, well, I need to create the actual container for this. So it's going to update the status and then tell Docker to download and run the Nginx container. And once Docker says that that's running, it will go ahead and update the status for our pod. So you can see that we went through here and we actually had 4 different controllers that were part of our kind of pipeline or part of our kind of workflow to deploy an actual application. So we had the deployment controller, the replica set controller, our scheduler, and our kubelet, all kind of working together to actually deploy an application. Okay. So the next thing we're going to talk about is kind of extending Kubernetes. So we'll essentially extend Kubernetes the same way that we would we build components as part of Kubernetes to extend it that are essentially the same as any other built-in component to Kubernetes. So kind of like in our spoke and wheel kind of diagram, we're just going to add new little stuff to the outside of the rim as part of the system in order to extend it. But kind of as you know, for most APIs, they have only certain set endpoints. You can't just normally add new endpoints to an API server without building your own API server or recompiling it or something like that. And so what we need is some sort of built-in mechanism to Kubernetes that allows us to extend the API. So what we need is a place to store our state. We need some sort of data, something that can store some data that we're going to use. And then we need something to do, implement that logic, right? So, we want to basically say this is what I want from the cluster, and then have something actually implement that. And so we can kind of do that in the same way as we did before, by having an object or having our data be an API object, and then have the logic be implemented by something like a controller. Excuse me. So Kubernetes has built into it something called a custom resource definition. And what this does is allows you to create a resource definition, which is essentially a new type in the API server. And so this declares a new type that the API server is going to be able to use. And then the API server then produces a new URL for the API server when you connect to it. And then you can use all the kind of same CRUD operations, so create, read, update, and delete, as well as watching for changes. So you get all of those same sort of functionality that you do from built-in objects with a custom resource. And so you can kind of describe higher level constructs, right? So to maybe take our example of memcache earlier, we might have a memcache cluster object, which describes a very high level construct or a very specific type of application that we want to deploy, right? And this could be like, anything that you can think of, like other databases or whatever. Other examples might be like creating certificates that get auto-updated or auto-refreshed. Basically any kind of object that you want to kind of create some sort of automation for. And you don't have to just use one object. You could have multiple custom resource definitions that work together. This is essentially how a lot of extensions to Kubernetes work, like Istio and things like that. So once we have our kind of resource and our data that we can save to kind of configure our application, we can then have our controller, which implement the logic that we need to have in order to automate the system. So our controller will typically just run as an application inside of the cluster and talk to the API server from within the cluster. And you can build these type of controllers in pretty much any language you want to. Anything that can kind of talk REST API to Kubernetes is fine. And there are many kind of client libraries out there. There's a bunch of them that are generated, like in Go and Python and Java, and other ones like in JavaScript and Ruby that are not quite as well supported yet, but there's a bunch of generated ones, as well as a single idiomatic client, which is the client Go library. And client Go is an idiomatic library that was originally built for Kubernetes itself. So all of the built-in pieces of Kubernetes use this library in order to talk to the API. And so what you'll typically see is that like controllers are written in Go because they want to make use of this client Go library. So client Go is like the most featureful. So from a practical standpoint, most controllers are written in Go, even though they don't necessarily have to be. And that's just because client Go is the most featureful client. And it provides a lot of extra functionality, not just a normal web API client library. It provides a bunch of other constructs that can be useful for creating things like controllers and whatnot. But it doesn't go, it goes far enough in the sense that you can use it as kind of a library or not necessarily even a framework, but like something that is, that can help you to kind of build a controller. So not just like a client library, but like kind of a controller library, if you will. However, the client Go library only goes so far. It doesn't provide you good ways of kind of getting rid of all of the, the tedium that comes along with creating controllers. So one of the things that you have to do when you create a controller is, create the definitions for the objects. So in Go you would create, a struct type for the objects and define all the fields, and then you would have to kind of use a code generator in order to generate the client libraries that are needed for that particular type. And this can be really, really tedious, and it's hard to manage, and it's hard to kind of understand how the client or the code generators work. So that's where kind of these like operator frameworks start to kind of become more useful. Because Go kind of doesn't have something like generics in Java, and it's a strongly typed language, when you're starting to add new types to the language, so these new types are the new types for our custom resources, right? So like our custom resource is, we get that from the API, and we have to translate that into a Go object. And so we have to have something like that built into our language, but we can't have that built into a really generic client library that can handle any type. Go just isn't quite that flexible, and so the way to do this in Go is by generating a bunch of code using a code generator. That can get a little bit unwieldy, and so there have been a couple of frameworks that have come out that try to make kind of generating and building these kind of projects for controllers and operators more friendly. So what these frameworks kind of do is provide kind of a simplified controller API. So like, they provide an even higher level kind of API than the client Go library does. Right? Client Go is fairly, provides a bunch of kind of building blocks or tools that you can use, but it doesn't make it really obvious like how to use those. And it also doesn't provide any way of avoiding a lot of the pitfalls that we'll talk a little bit about later. So what these do is they provide a very simplified controller API to kind of help people avoid a lot of problems that happen with controllers, as well as manage generate and manage the code that you are going to generate for these applications. So one of the problems that controllers tend to run into that these libraries help with is making frequent requests to the API server. So typically, these controllers will run in a loop, and this loop is can be rate limited if you really want it to be, but that's kind of up to the. It can be kind of tedious to manage all of the controllers that are running in the cluster. And so generally what in order to avoid overloading the API, the controllers will do a lot of caching of data. So it will say get a bunch of the objects that it cares about and cache them locally, and then just watch the API in case any of them change. So you have a local cache, and then if any of the objects that you're watching change, or you have cached changes, that watch API will then tell you which ones have changed and how they've changed, and so you can just update the cache. And so this typically makes the API server, or gives the API server a little bit more headroom in terms of its its performance, or it doesn't overload the API server. So these libraries kind of help with that sort of thing, and allowing you to do that somewhat transparently. Also, these libraries and frameworks help you deal with things like concurrent updates. So if you have a particular object or a particular custom resource, and then you want to perform some action based on when that custom resource is created or changed, typically you don't want to have multiple controllers or multiple loops running that will act on those changes at once, right? That can be, you can run into kind of race conditions and things like that. And so typically from when one particular object changes, you want to have any logic that runs from that particular, or that results from that particular object's or instance's change to happen in a serial manner. And so these will help you to be able to deal with kind of concurrent updates, or to avoid concurrent updates to a single object within Kubernetes. So it's worth saying that you can, for a single custom resource definition or type, you wouldn't do all of the updates for all of the instances of that type serially. You just want to be able to do for each individual instance or each individual custom resource, you want to be able to deal with serially. So custom resource A and custom resource B, even though they're the same type, you can have those processed parallelly, but you don't want to have two different controllers running and processing custom resource A in parallel, because that can cause problems. And that flows from the fact that the API server is not really a full-fledged database or anything like that. It doesn't really have transactions or things like that. So you have to be somewhat careful about how you, you interact with it. All right. So the first framework that I want to talk about is the operator SDK. And this was built by some folks at CoreOS, which had by that time become Red Hat already. Or had been bought by Red Hat already. So these are, former CoreOS folks who had moved to Red Hat. And so what the operator SDK is like, it's a fairly simple kind of application or SDK that you can use to build kind of an operator or a controller application. But it's somewhat, it's kind of quick and dirty or somewhat limited in its feature set in that it provides support for running one controller per project or per process. And basically being able to support essentially one CRD. So if you have something that's fairly simplistic, you're creating one CRD and then you're just doing, you're doing something fairly simple for that particular as a result of the creation of that particular CRD, then that can be maybe handled by the operator SDK. But if you want to create something that's a little bit more complex and uses kind of built-in types or uses multiple CRDs, then the operator SDK is somewhat limited in that sense. All right. So I can maybe show this a little bit to show what it looks like. But essentially, it's kind of, if you're familiar with applications that scaffold out code, it's very similar to something like that. So if you do oops. Went back in my history too far. Okay. So here, I can create a new application, and what this will do is it'll spit out a bunch of generated code, basically a scaffold for a particular type, and I basically just give it the API version and the type of the name of the CRD that I want to create, and then it scaffolds out the operator, some basic code for that, and the type, as well as the API clients for it. And then what it's doing right now is running a dep ensure that pulls down all the dependencies. So this will take a minute or two. And then it writes out some other kind of scaffold stuff. So a nice Docker file and make file that you can use. So if we take a look at the actual command that I just ran, I gave it the name app operator, and then I provided this API version. So we talked about the API version being part of an API object in Kubernetes. So here we're specifying our kind of custom domain and version number for our object, and then the kind is just app. And so what we'll do here is just look at this generated. And so it generated a bunch of code here, and which kind of helps us to manage a particular project. If we look in config, we'll see some, let's see, actually no, it's in deploy, I think. We'll see that it generated a CRD for us, and this CRD is deploy CRD. This is a generated custom resource definition with the name. So in this case, we gave it the name, the type or the kind was an app, and then app.example.com was the group. So it puts together that as a name of my custom resource. And here we have the app.example.com group and the kind being app. And then there's a couple of other fields in here, like what the list kind is, or like things like that, which are not particularly interesting. But one thing that's interesting to note here, though, is that like this scope here is namespaced. So if you're familiar with namespaces in Kubernetes, they're kind of a way of segmenting things, and you can create objects that are either saved per namespace or are cluster-wide. And so some things like, so you might create some custom resources that might be something that you want to be a cluster-wide thing that doesn't act per namespace. In those cases, they're generally things for like maintenance, cluster maintenance, or things like that. But it's just useful to know that in this case, we're actually creating a scoped, a namespace scoped object. And then if we look in here, we can see like that it's created a package. And if we go into APIs, we can notice that it's created the actual types here. So if we go into types, we'll see like app list is like a list of objects, and then here's our app type that it's generated for us. And then in here we can fill out like the actual fields that we need for our application. And then status is something that's generally is a convention used to update like the status as to how far along the controller is in terms of implementing or implementing my desired state in the cluster. Okay. I think I'm in the right spot now. Okay. If we go into stub, we can see that we've got this little handler thing. And this is actually going to show our, there's going to be our kind of loop logic. So in this case, we have this event that comes in. So this is essentially like an object change. So whenever my custom resource changes, like this handle function will get called, or this handle method will get called, and then I can essentially implement like any kind of logic that I want to inside of here. So in this case, what it's doing is it's going to say like, it's going to create some sort of busybox pod by default here. And so what I can do is I can kind of, overwrite this code with whatever code that I want to implement my application. All right. All right, back to the head here. Okay, so the operator SDK is okay, but like it allows us to just basically create one controller per CRD and create an application that watches for changes for that CRD and implement some sort of logic. Okay. But that's somewhat limiting. Like if I wanted to do my kind of memcache example, there's several things that I want to do there. I don't necessarily want to implement all the logic for it in one single control loop. I might want to watch many different types of objects, some of them built-in objects like deployments or services or things like that. So some of the architecture patterns that you see, like in real life, are like things like reuse of the built-in objects. So like as part of your controller's architecture, you might reuse things like deployments or reuse things like services or config maps in order to deploy some sort of application. Sometimes that might be a database or a memcache or something like that. And you don't want to have to implement everything yourself. And so you want to reuse some of the built-in objects to get the functionality out of those objects. And so a lot of times you want to check for changes in those objects to kind of like reconcile that with what you actually expect to be there and things like that. And so you want to have some way of watching those and having controllers that act on those as well. So another kind of example or another kind of pattern that you will see in these kind of operators is to have multiple controllers or multiple control loops in a single application or a single binary. And the reason that you see this is because if you have a single control loop, that control loop can get bogged down doing some sort of work in one single control loop, and then either be delayed in its like overall kind of processing, or you know, you don't want it to necessarily have to wait for one particular thing to happen before you do some sort of other kind of unrelated logic. So you can kind of keep unrelated things in separate controllers. So that's something that another framework called KubeBuilder allows us to do, and that's and KubeBuilder is built by some developers at Google, so actually folks that work on the Kubernetes team. And KubeBuilder is a little bit more robust in that it helps us manage it allows us to support controllers for built-in objects as well. So it can allow us to watch, say, deployments for changes. And it allows us to build multiple controllers into a single project or binary. And it also helps like us manage the life cycle of the project a little bit better. Like say like the client Go library changes and we want to update our app to be able to use the new version, and then we need to re-update like all of our generated code and all of that stuff. Like that can be kind of a pain if you have to do it yourself. And so KubeBuilder provides some functionality to do that. So let's look at an example. So like first we're going to make and then if we do KubeBuilder init, here we're going to just we're going to init a project, and we're going to give it the domain of k-io. So this is part of our API version. We're going to give it a license and an owner, so that just stubs out some licenses. And then let's not do that. And then, so normally you would run dep ensure here to populate all of the vendor dependencies and whatnot, but I'm just going to skip that for time's sake. And then what you can do here is run something like create API, which will then create a particular type for your controller, as well as stub out a controller for that particular type. So in this case, I can create one that looks at a built-in type and then acts based on that. So in this case, when I run this, I don't need to create the resource. I can say no, but I can create a controller that runs underneath the project. And this is a little bit funny because it generates some code that doesn't compile right off the bat, but that's kind of an easiest fix. But if you see something like, if you go look at this thing, we can see that it does something similar to what the operator SDK did, in the sense that it gives us some stubbed out code that we can then, let's see. So here, generally in this reconcile part here, we can implement the logic for our particular controller, so that whenever something changes, we can, act on that particular change. All right. So that's kind of how KubeBuilder works, and then KubeBuilder provides some other features like builder. So in here, there's an update command, which helps us to do things like update vendor dependencies and whatnot. So this can be kind of a little bit more helpful for managing the overall project. All right, so that's pretty much everything I had for this particular talk. Hopefully that was helpful, and I recommend you check out both Operator SDK and KubeBuilder as if you're looking to extend Kubernetes and find out more about how to kind of interact with the API and build this kind of automation for container infrastructure. Thanks a lot.
質問がある方、挙手をお願いいたします。質問ありますでしょうか。
race condition with multiple controllers.
Right.
So how do you prevent two concurrent controllers maybe running because Kubernetes could know about one certain second from modifying results?
Yeah, so, okay. So the question is like whether you, how do you prevent multiple controllers from running? And generally what you do is you just run one instance of a controller at any particular time. And then you can, so if you want to have like high availability for a particular controller, you can basically do hot standbys for the controller. So like you just basically have like, you have something like leader election where you have one controller or one application instance running that's actually performing the control loops. And if that kind of goes away in any sense, then, or if that crashes or stops working, then another one can be elected the leader and then continue processing. And that's done through the API as well. Like, so one of the kind of patterns is that you pretty much store all state for any of these things in the API server. And so that way you kind of avoid some of the issues that you would have with these type of leader election issues and whatnot. Like having two masters come up or whatever. That's generally done through the API server. Yeah, it does. So it has like a way of saying like if this particular object was modified at a so you're saying like you say like, okay, I'm modifying version 2 of this particular object, and if some other guy makes a change to it, it gets updated to version 3, and so that version, those versions get compared when you actually make a change to the object. Yeah.
はい、他に質問は